Welcome back, everybody. All right, we have a new lesson today in weather, meteorology. And today we're going to be discussing the relationships that occur between various weather variables that we've already learned about or will learn about. Now, these relationships are important because they determine many factors that control the weather. So first, let's start off, and I have a bunch of these fill-ins today. Kind of makes more sense to tell the story of all this than just to explain a few random things and try to put them all together. So as air cools down, we know it loses some of its kinetic energy, and those molecules of N2, which is nitrogen, O2, oxygen, and CO2, carbon dioxide, and water vapor, they slow down. This energy loss causes more water vapor to condense. Remember, less energy, it condenses into a liquid that can stay evaporated as a gas. The end result is that cold air has more water vapor always condensing than evaporating, and therefore it has less overall potential water vapor content in the air. So it's less possible for the water vapor to be in the air as it cools down than it is when air is warmer. And let's go through the opposite here. Air warms up, it gains the kinetic energy. Those molecules start vibrating faster or moving faster, and they speed up. This energy gain causes more water vapor to evaporate. So you have a surface like a lake or a pond, more water molecules have the ability to evaporate into the air, into a gas than can condense as a liquid. The result is that the warm air has more water vapor evaporating than it does condensing. So these things are always happening concurrently at the same time, but there's more of the evaporation in the warmer air than it's condensing. The picture below represents water vapor molecules above a lake on 2 different days. And you can see that on the left side here, we have a cool day, and there's not as much ability for these water molecules to escape the liquid into the air, and so there's only like 3 of them here. On the warm day, there's a whole bunch because the temperature allows that water to escape into a gas more easily. What statement can you make about the potential for humidity in the air versus temperature? Well, we know that because of this whole fact that we just learned about, that the warmer the day, the more the potential for evaporation and water vapor to go into the air. And so our graph would look something like this. The relationship is that as temperature increases, the amount of water vapor potential in the air also increases. Doesn't mean it has to go in the air because there might not be any water to evaporate. But, around here there is. And here's just summing it up. Warm air has a higher potential to hold water vapor than cold air, and that's exactly why some summer days, and you know what days I'm talking about in the summer, can feel so uncomfortably humid, oppressively humid. The warm air truly does, on those days, contain way more water vapor than it could on an equal amount of cold air. That's when you sweat, and it just doesn't evaporate, so it really feels uncomfortable. Another cool fact, when air is saturated at 100% relative humidity, it can't get any more saturated. It's already as much as it can. I don't want to say holding, but it's containing 100% of what it can at that temperature. In other words, if you try to evaporate more water vapor into the already saturated air, it immediately condenses back out into a liquid. And that's why you do feel uncomfortable on those days, like the guy on the right. Okay, next factor, air pressure versus temperature. And here's another little story. As air temperature rises, those molecules again move farther apart. Remember, they're moving faster, so they spread out. Since the atmosphere is not like a container holding these gases in, they speed up and fly farther apart. The end result is fewer molecules in any given area to exert pressure and a drop in air pressure because of that. So the weight of air pressure pressing down becomes less. In contrast, you cool off that air, it results in a rise in air pressure. And that's because those air molecules are closer together, they're not vibrating as fast or bouncing around as fast, and there's more of them in a given volume, and they weigh more, so there's more air pressure. And you can see that in the pictures over here. Cold air, a lot more air molecules pushing down on the earth, and so more air pressure. A warm day, there's only a few, there's not very many, and so low air pressure. So high when it's colder, low when it's warmer. And here's a graph showing that relationship. And you can see here the pressure is in blue and the temperature is in red. And just, we'll focus on one area here in general because it's day-to-day temperatures up and down here. But if we look at this general trend in temperature, let's plot that general trend. These are over many days. And let's focus specifically on these days in this area. You notice it's a little cooler here than it is over here or over here. And when it's cooler, look what happens to that air pressure. The air pressure is high. And so what I just taught you on that previous slide is shown here in an actual weather graph here of temperature versus pressure. And you can see the opposite. As the temperature overall kind of goes up, the pressure drops. And there's the simplified graph. As temperature increases, pressure decreases. Moving on. All right, here we have a graph for an area near Earth's surface during a 12-hour period. You can see that from 6 a.m. to noon and then to 6 p.m., the air temperature is going up like that. And the question is, what's the air pressure graph going to look like? And remember, they are kind of opposite. So you want to look for the one that's like the exact mirror image opposite. In that case, choice D. Okay, next one is air pressure versus altitude. This is a very easy weather relationship to understand because air molecules have mass, therefore they have weight under Earth's gravity. And you can see all these molecules, most of them are down here near the Earth's surface because gravity is pulling on them just like it's pulling on you right now. And most of them end up moving downwards towards the Earth's surface. And there's less of them up higher. So if you were to measure how much weight is above you down in this area of air molecules pushing down on you, there's a lot more because there's a lot of space between you and space. But if you're on top of this mountain, there's less air pressure because there's less air above you at that point because you're higher up by, whatever that elevation is right there. And that's why as you go up and down mountains or even big hills in cars, you can feel your ears pop. It's just the pressure equalizing. So the force of gravity pulls most air molecules close to the Earth. This results in more air molecules and more air pressure near Earth's surface and less air molecules and less air pressure far above Earth. Okay, that's an easy one to understand. And you can see it in the reference tables represented right here on the Earth's surface, which is this bottom line right here. As you go up, the air pressure drops off. It doesn't quite get to zero, but it comes really close. And this stands for 1 atmosphere of air pressure there. Okay, and then in the last weather relationship, air pressure versus humidity. And let's start with the fact here. One water vapor molecule weighs less than an average molecule of air. This is something that goes, it's kind of counterintuitive. You'd think that the air molecules would be lighter than the water vapor molecules. But it turns out, or the air molecules would be, lighter than the water vapor molecules. But it turns out that water vapor is actually much lighter than an air molecule. And you can see the masses I put up here. These are average atomic mass units of air molecules versus water vapor molecules. And they are quite different. Water vapor is quite a bit lower. And if we check out this sentence down here, this means that air at 100% relative humidity has lots of the lighter water vapor molecules and less of the heavier ones. So if you fill up air, as well, you don't want to really think of it as filling it like a container, but if you add a lot of water vapor to the air, those water vapor molecules displace the air molecules, and not all of them, but a bunch of them, and therefore you have less mass overall because those water vapors are lighter. So the result, moist air is lighter and therefore less dense and lower in air pressure. There's less weight of that air than in the dry air, which is heavier, more dense, and higher in air pressure. And you can see that in the picture up here. These little circles represent the water vapor molecules which have displaced or taken the place of the other molecules that were up in this picture, and they're now lighter here. Well, at least these moisture, water vapor molecules are lighter, So the overall air is lighter, and that means the pressure is lower, pushing down on us than when it's drier air, which has higher air pressure. So I guess you could remember it high and dry. And this kind of demonstrates the same thing. You can see the water vapor. It's only 18 grams in this particular sample over there. It's you know, a bunch of air stuck on a balance. And let's see, carbon dioxide 44 grams, oxygen 32, nitrogen 28. The big point here is, guys, that the water vapor is so much less mass than the others. And if you replace the others with that, of course the air is going to be lighter and lower in air pressure. Which graph best shows the relationship between the atmospheric pressure and the water vapor content at Earth's surface? So let's take a look at the x-axis. As water vapor increases, we know that the air should become lighter and lighter, and therefore it's not pushing down as much. The pressure should be lower. So this graph is not correct. Water vapor increases, it should be getting lower. Nope, nope. But here we see as water vapor goes up, the air pressure drops, and that is the correct choice. So it's an inverse relationship, and that is it. All right, guys, these are kind of complicated. Weather relationships can be a little tricky. It's a lot of conceptual information here. So